Welcome to this webinar on AI in industrial automation, how smart algorithms are transforming Industry 4.0. My name is Matt Lonbani from InnerAutomation, and over the next hour, I'll be guiding you through a practical and strategic exploration of how artificial intelligence is reshaping the industrial landscape. Whether you're an engineer, manager, or executive, this session will help you understand where AI fits into your automation systems, how to identify use cases, and what steps to take to implement AI-driven solutions effectively. Let's get started and unlock the potential of AI for your factory, production line, or automation business. Before we dive in, here's a quick look at what we'll cover in this session. We'll begin with an overview of industrial automation and how AI fits into the evolution toward Industry 4.0. Then, we'll explore the core AI technologies that are most relevant to industrial environments, things like machine learning, deep learning, computer vision, and more. Next, we'll walk through real-world applications of AI in factories covering use cases such as predictive maintenance, quality inspection, and process optimization. We'll look at case studies across industries like automotive, pharmaceutical, and energy to see how AI is being applied in practice. Then, we'll go into implementation, how to actually bring AI into your control systems, and what to look out for in terms of data, integration, and security. We'll also talk about challenges like data quality, workforce readiness, and the need for explainable AI. Finally, we'll look ahead at future trends, autonomous systems, self-healing machines, and the role of generative AI before closing with clear, actionable steps you can take after this webinar. Let's begin with a foundational understanding of what industrial automation is and how it's evolving with AI. Industrial automation is the use of control systems like PLCs, computers, and robots to operate machinery, perform repetitive tasks, and manage complex processes without continuous human intervention. The main goals of automation have always been consistent: improve safety, increase speed, reduce human error, and make production more efficient and scalable. Traditionally, automation relied heavily on fixed logic and pre-programmed instructions. Think of classic ladder logic in a PLC or rigid machine cycles designed for mass production. But as systems grow more complex and demand increases for flexibility, real-time adaptation, and cost efficiency, traditional automation alone often falls short. This is where AI begins to make a difference, by turning rule-based machines into systems that can learn, adapt, and optimize themselves. Understanding this shift from static to intelligent automation is key to seeing how AI adds value across the entire industrial ecosystem. To understand the role of AI in today's industrial landscape, let's look at how we got here through the four industrial revolutions. Industry 1.0 introduced mechanization with steam and water power. This was the age of the mechanical loom and the first factories. Industry 2.0 brought electricity and mass production. Assembly lines revolutionized output, and manual labor began to shift toward machine operation. Industry 3.0 introduced electronics, computers, and PLCs, bringing about the first wave of digital automation in manufacturing. Today, we are in Industry 4.0. This revolution is powered by smart technologies, AI, the industrial Internet of Things, cloud computing, and cyber-physical systems. It's not just about automating tasks, it's about making systems intelligent. Machines that learn, processes that optimize themselves, factories that talk to each other. Industry 4.0 marks a major shift from control logic to adaptive intelligence. And AI is the technology at the heart of that transformation. Artificial intelligence, or AI, refers to systems that can mimic cognitive functions, things like learning, problem-solving, recognizing patterns, and making decisions. In an industrial context, AI is what allows machines to go beyond pre-programmed instructions. Instead of just following logic, they analyze data, identify trends, and adapt to changing conditions. There are several branches of AI relevant to automation. First, machine learning. This allows systems to learn from historical data and improve over time, without being explicitly programmed. Second, computer vision, used to interpret visual input from cameras for things like quality inspection and object detection. Third, natural language processing, or NLP. This enables machines to understand and respond to human language, which is helpful in interfaces, reporting, and diagnostics. And finally, there's decision-making AI systems that can choose the best course of action in real time based on complex input. AI doesn't replace your automation system, it enhances it. It's an overlay that brings adaptability, prediction, and insight to the deterministic world of industrial machines. Automation and AI are not the same, and that's important. Traditional automation is rule-based. It follows fixed instructions like if X happens, do Y. AI, on the other hand, is data-driven. It recognizes patterns, makes predictions, and improves with feedback. Together, they are powerful. Automation ensures consistency and speed. AI adds flexibility and intelligence. For example, a traditional PLC might trigger an alarm and stop a machine when a fault occurs. But an AI-enhanced system can analyze patterns in vibration, temperature, or pressure to predict that fault hours or even days in advance. AI can also adjust process parameters on the fly based on real-time data, something that traditional systems can't do without manual tuning. And in robotics, AI enables machines to make decisions in uncertain environments, like how to pick and place objects with varying shapes and orientations. So, when AI and automation work together, the result is a system that's not just reactive, but proactive and even autonomous. So far, we've looked at the fundamentals of industrial automation and how AI fits into the picture. What we've seen is that automation gives us the structure, reliability, repeatability, and control. But AI adds something more: intelligence. By combining the two, we move beyond hardwired processes to systems that can learn, adapt, and continuously improve. This is the foundation of the smart factory, where machines don't just follow instructions. They anticipate needs, optimize operations, and evolve with time. Whether you're just beginning your digital transformation or already deploying AI at the edge, understanding this synergy between AI and automation is key to unlocking the full potential of Industry 4.0. In the next section, we'll explore the core AI technologies that are enabling this transformation, from machine learning to computer vision and beyond. Now that we understand how AI enhances automation, let's take a closer look at the key AI technologies driving industrial innovation. First, there's machine learning. This is the backbone of most industrial AI systems. It enables algorithms to detect patterns in data and make predictions or decisions without being explicitly programmed. Then we have deep learning, which is a subset of machine learning. It uses neural networks to analyze large volumes of unstructured data, such as images or sensor signals, and is especially powerful in complex environments. Another core technology is computer vision. With the help of cameras and AI models, it allows machines to see and interpret visual information, making it ideal for defect detection, quality inspection, and safety monitoring. Next is natural language processing, or NLP. This helps machines understand and generate human language. In industry, it's used in report generation, intelligent diagnostics, and even voice-activated interfaces. And finally, reinforcement learning, a technology that helps AI agents learn optimal behaviors through trial and error, especially useful in robotics and dynamic process environments. These core technologies serve as the digital building blocks of intelligent automation. In the next few slides, we'll break each one down with practical examples from the factory floor. Machine learning is one of the most widely used AI technologies in industrial environments, and for good reason. At its core, machine learning allows a system to learn from historical data and make predictions about future outcomes. This is incredibly valuable for applications like predictive maintenance, energy forecasting, and anomaly detection. For example, a machine learning model can analyze vibration and temperature data from a motor over time and detect patterns that lead up to a failure. Once trained, it can then alert operators when similar patterns emerge, helping avoid costly downtime. ML is also used to optimize process parameters. Instead of an engineer constantly adjusting set points, a machine learning algorithm can find the ideal combination of settings that maximize yield and minimize waste. What makes ML powerful is its ability to continuously improve as it sees more data. This creates a feedback loop where the system gets smarter and more accurate over time. Whether running in the cloud, on-premise, or at the edge, machine learning is foundational for unlocking industrial intelligence. Deep learning is a specialized type of machine learning that uses artificial neural networks to process and learn from vast amounts of unstructured data. In industrial settings, it excels at tasks that are too complex for traditional algorithms, especially when dealing with images, time series signals, or multidimensional sensor data. One of the most impactful applications of deep learning is in visual inspection. Instead of relying on rigid rules, a deep learning model can learn from thousands of labeled images to detect subtle defects that might be missed by the human eye or traditional vision systems. It's also used for anomaly detection in complex machines, where the data patterns are nonlinear and constantly changing. For example, in a compressor, deep learning can recognize tiny deviations in waveforms that precede mechanical wear or imbalance. Deep learning powers real-time decision-making in advanced robotics as well, such as when a cobot needs to understand its environment and adapt its movement accordingly. Although deep learning models require more computational power and data to train, their ability to generalize and self-tune makes them a critical asset in modern industrial AI solutions. Computer vision enables machines to see and interpret visual data much like a human would, but with more precision, speed, and consistency. In industrial automation, computer vision has revolutionized quality inspection. Cameras paired with AI models can detect surface defects, color deviations, missing components, or misalignments in milliseconds far beyond the capabilities of human inspectors. It's also used in safety monitoring. For example, vision systems can track human movement in a workspace and trigger alerts or shutdowns if someone enters a restricted zone. Computer vision supports robotic guidance as well. It helps robots locate, identify, and interact with objects such as picking parts from a conveyor or placing labels on products. What makes AI-powered vision systems different from traditional ones is their adaptability. They don't rely on fixed rules. Instead, they learn from real-world variations, different lighting conditions, angles, shapes, or textures. This flexibility allows for more reliable inspection, greater automation, and fewer false positives, ultimately improving both product quality and operational efficiency. Natural language processing, or NLP, allows machines to understand, interpret, and generate human language, both written and spoken. While it might seem more relevant in consumer tech, NLP is rapidly gaining ground in industrial environments as well. One of the key use cases is automated documentation. NLP can analyze logs, maintenance reports, and operator notes to extract insights and even generate summaries or alerts based on recurring issues. Voice-enabled interfaces are also becoming more common. Imagine a technician saying, "Show me the latest fault report," and the system instantly retrieving and displaying the data hands-free. NLP also powers intelligent chatbots in manufacturing environments. These can assist workers in troubleshooting, pulling up part specifications, or navigating technical documentation without needing to dig through manuals or databases. And when it comes to compliance, NLP helps automate the reading and processing of lengthy regulations or SOPs, flagging inconsistencies or suggesting updates. In short, NLP bridges the gap between human expertise and machine intelligence, making it easier for people to interact with complex automation systems. Reinforcement learning, or RL, is an advanced branch of AI where systems learn by interacting with their environment and receiving feedback through rewards or penalties. Think of it like teaching a robot to walk or balance by trial and error. Over time, the system learns the best strategies to achieve its goal. In industrial automation, RL is especially useful in dynamic environments where conditions constantly change and the optimal response isn't always obvious. For example, a reinforcement learning algorithm can control a robotic arm that needs to adjust its grip and movement depending on the weight, size, or position of a part. It's also applied in process control such as managing the temperature, pressure, and flow in a chemical plant to optimize output while minimizing energy use and waste. What sets RL apart is that it doesn't need labeled data, it learns by doing. That makes it ideal for simulations or scenarios where experimentation is safe and repeatable. As computing power grows and simulation tools become more accessible, reinforcement learning is poised to play a much larger role in adaptive, autonomous control systems across industry. Let's quickly recap the core AI technologies that are transforming industrial automation. First, we have machine learning, which helps systems learn from historical data and make accurate predictions. Then deep learning, a powerful form of machine learning used for processing complex inputs like images, waveforms, or signals. Next is computer vision, which enables machines to visually inspect, detect defects, and guide robots in real time. We also looked at natural language processing, which helps machines understand and interact using human language, making interfaces more intuitive and efficient. And finally, reinforcement learning, which allows systems to learn optimal control strategies by trial and error, perfect for dynamic or simulated environments. Together, these technologies form the backbone of intelligent automation, allowing systems to not just act but to think, adapt, and improve. Now that we've explored the tech, let's see how these tools are being applied in real-world industrial settings. Predictive maintenance is one of the most impactful applications of AI in industry. It shifts maintenance from a reactive or time-based schedule to a condition-based, data-driven strategy. Instead of waiting for a machine to fail or replacing parts at fixed intervals, AI models can analyze sensor data to forecast when a component is likely to break down. For example, by monitoring vibration, temperature, current draw, or acoustic signals, AI can detect subtle signs of wear long before a human would notice. This enables companies to schedule maintenance exactly when it's needed, avoiding unplanned downtime, reducing spare parts inventory, and extending equipment life. Machine learning models become more accurate over time, learning from both failure events and healthy operation data. And with edge computing, these predictions can be made directly on the shop floor, enabling real-time alerts and actions. Predictive maintenance not only improves reliability, it transforms maintenance from a cost center into a strategic performance driver. Quality inspection has always been critical in manufacturing, but traditional methods are often slow, inconsistent, and expensive. AI is changing that. With computer vision and deep learning, machines can now inspect products at high speed with incredible accuracy. Instead of relying on fixed rules like pixel thresholds or rigid templates, AI models learn from real defect samples. They can detect cracks, surface scratches, label misalignments, or missing parts even under variable lighting or from different angles. This makes inspections more reliable, especially in high-mix, low-volume production environments where products often vary. AI inspection systems also reduce false positives, so you catch only the actual defects and avoid wasting time on perfect parts. And because these systems continuously learn and improve, they adapt to changes in design, materials, or production conditions. The result is better product quality, lower scrap rates, and faster response to process deviations, all without adding labor. In many industrial processes, even small improvements in efficiency can lead to significant gains in output and cost savings. AI helps unlock these improvements by continuously analyzing data from across the production line and identifying optimization opportunities in real time. For example, a machine learning model can monitor variables like temperature, speed, flow rate, and pressure and adjust set points to maintain optimal performance. This isn't just control, it's intelligent optimization. AI can detect inefficiencies that might go unnoticed by traditional systems or human operators. It can help reduce cycle times, minimize energy consumption, improve yield, and balance quality against throughput automatically. In chemical plants, food processing, metal cutting, or packaging lines, AI can be used to tune hundreds of parameters in ways that are impossible to do manually. And when integrated with MES or EIP systems, optimization extends beyond the machine to the entire process chain. AI transforms process tuning from a one-time setup task into a continuous improvement engine. AI is revolutionizing robotics in manufacturing, making machines smarter, safer, and more collaborative. Traditional industrial robots are fast and precise, but they operate in rigid, pre-programmed paths, usually behind safety fences and far from human workers. AI changes that. With computer vision, machine learning, and real-time sensing, robots can now adapt to changes in their environment. For example, AI-enabled robots can recognize and pick items of varying shapes and orientations without needing reprogramming. And with reinforcement learning, robots can optimize their own movements, finding the fastest, safest, or most efficient way to perform a task. Cobots, or collaborative robots, take it a step further. They work safely alongside people, adjusting their behavior in response to human presence. AI ensures these cobots are not just safe, but intelligent, able to hand off tasks, follow voice or gesture commands, and support operators in assembly, testing, or inspection. This blend of flexibility and intelligence is what makes AI-powered robotics a key enabler of agile, human-centric manufacturing. Supply chains are the lifeblood of any industrial operation, but they are also incredibly complex and vulnerable to disruption. AI brings much-needed intelligence to this space by enabling accurate, real-time forecasting and decision-making. Machine learning models can analyze historical demand, production cycles, lead times, weather data, and even geopolitical events to forecast supply chain needs more accurately than traditional planning tools. This helps manufacturers predict material shortages, optimize inventory levels, and avoid overproduction or underutilization. AI also supports dynamic route optimization and logistics planning, recommending faster, cheaper, or more reliable delivery paths based on real-time conditions. And when unexpected changes occur, like a supplier delay or a sudden spike in demand, AI systems can suggest alternate plans instantly, helping companies stay agile. Ultimately, AI in the supply chain improves visibility, reduces risk, and ensures that production stays aligned with real-world market demands. Let's recap some of the most powerful ways AI is transforming industrial operations. We started with predictive maintenance, using AI to detect equipment issues before they cause downtime. We then explored quality inspection, where AI-powered vision systems spot defects faster and more reliably than humans. In process optimization, AI adjusts parameters in real time to maximize efficiency, reduce waste, and improve consistency. We also saw how robotics and cobots become more intelligent and adaptable, with AI able to collaborate safely with humans and handle variability on the fly. And finally, supply chain forecasting, where AI brings clarity and foresight to procurement, logistics, and planning. These are just a few examples. The real power of AI lies in its versatility, its ability to bring value across multiple layers of industrial operations. Now, let's take this understanding a step further by looking at real-world case studies across different industries. Let's start with the automotive sector, one of the earliest adopters of AI in manufacturing. In modern car factories, AI is used extensively for visual inspection. Deep learning models detect paint defects, assembly errors, and microcracks in body panels faster and more accurately than human inspectors. On the production line, AI-enhanced robotics ensure precise assembly, torque control, and alignment, while cobots assist human workers in tasks that require both dexterity and strength. AI is also transforming predictive maintenance for welding robots, conveyors, and paint booths, reducing downtime and improving OEE across the plant. Beyond the factory floor, AI powers part traceability, logistics optimization, and even quality prediction, helping manufacturers meet strict compliance standards and reduce warranty claims. In the automotive world, where margins are tight and precision is critical, AI delivers measurable value at every stage of production. In the pharmaceutical sector, quality, compliance, and traceability are everything, and AI is playing a vital role in meeting those demands. AI-powered vision systems are now used to inspect blister packs, vials, and labels with extreme precision, detecting contamination, fill-level errors, or misprints that might compromise safety. In batch manufacturing, machine learning models monitor real-time data from bioreactors and mixes to identify anomalies and maintain process integrity. AI is also enabling predictive maintenance on critical equipment like centrifuges and HVAC systems, ensuring sterile conditions are preserved and reducing the risk of production halts. Another area of impact is regulatory compliance. Natural language processing helps parse and verify thousands of pages of regulatory documentation, streamlining audits and reporting. In short, AI in pharma enhances both safety and efficiency, allowing companies to meet stringent standards while scaling production more effectively. In the food and beverage industry, consistency, speed, and hygiene are non-negotiable, and AI is helping meet all three. Computer vision systems inspect products like baked goods, bottled drinks, and packaged meals for size, color, shape, and labeling accuracy in real time. AI-powered defect detection ensures that only products meeting exact standards make it to the shelf, reducing waste and customer complaints. Machine learning models are also being used to optimize filling operations, reducing spillage and overfill, while improving throughput. In refrigeration and cooking processes, AI algorithms monitor temperature and timing to maintain food safety and energy efficiency, especially in high-throughput environments. AI helps predict demand based on seasonality, local events, or weather data, enabling smarter inventory and supply chain decisions to reduce spoilage. And most importantly, AI systems are designed to operate in hygienic environments with minimal human contact, supporting both safety and automation goals. The energy and utilities sector faces challenges in reliability, safety, and efficiency, and AI is helping meet those challenges head-on. One of the key uses of AI here is demand forecasting. Machine learning models analyze consumption patterns, weather data, and market behavior to predict energy needs at the grid level, ensuring balanced supply and demand. In power plants and distribution networks, AI monitors equipment health using vibration, thermal, and acoustic signals, enabling predictive maintenance on turbines, transformers, and pumps. Smart meters and IoT devices provide real-time data to AI systems, which then optimize load distribution, detect leaks, and even prevent blackouts through automated decision-making. In renewable energy, AI helps manage the variability of solar and wind generation by forecasting output and adjusting the load dynamically. AI also assists in compliance and reporting, especially for sustainability metrics and emissions targets. From improving grid reliability to optimizing energy use, AI is rapidly becoming the brain behind the modern power system. In the semiconductor industry, precision is everything. Even a microscopic defect can lead to costly product failures or recalls. AI plays a critical role in wafer inspection. Using high-resolution imaging and deep learning, systems can identify pattern defects and surface anomalies that traditional rule-based systems might miss. During production, AI monitors and controls hundreds of variables in lithography, etching, and deposition processes, ensuring uniformity across millions of chips. Predictive maintenance is also key. AI analyzes vibration, vacuum pressure, and tool wear to forecast failures in high-precision equipment like ion implanters or chemical mechanical polishers. Yield optimization is another major benefit. AI correlates process parameters with final test results, helping engineers tweak recipes to reduce scrap and improve first-pass success rates. Because the semiconductor industry operates at nanoscale tolerances with massive volumes, AI's ability to process huge datasets and spot invisible trends makes it an indispensable tool. Let's wrap up this section with a quick summary of where AI is making a tangible impact across industries. In automotive, AI enhances visual inspection, robotic precision, and predictive maintenance, supporting high-throughput, high-precision production. In pharmaceuticals, AI ensures compliance and batch quality, improves sterile operations, and automates documentation workflows. In food and beverage, it boosts inspection accuracy, optimizes process control, and reduces waste in highly sensitive production environments. In energy and utilities, AI forecasts demand, enables predictive maintenance, and optimizes grid operations with smart, adaptive control. And in the semiconductor industry, AI ensures defect-free production, improves yield, and prevents downtime in extremely complex and sensitive processes. What we see across all these cases is a common pattern. AI adds intelligence to every layer of the value chain, from raw materials to delivery. Now let's move into the next section: how to actually implement AI in your own industrial environment. Now that we've seen the potential of AI in real-world settings, the question becomes, how do you implement it in your own automation projects? The first step is recognizing that successful AI implementation isn't just a technology decision, it's a strategic one. It involves aligning your technical goals with business outcomes. Start by identifying specific problems where AI could add value, like reducing downtime, improving inspection accuracy, or optimizing process efficiency. You'll also need to assess your data readiness. AI requires quality data clean, labeled, and accessible. That means having a clear picture of what sensors, systems, and historical records are available. Next, assemble the right team. AI projects succeed when OT professionals, automation engineers, IT staff, and data scientists work together. And finally, begin with a pilot. A small-scale project with a clear goal allows you to prove value, build internal confidence, and refine your approach before scaling. With the right foundation, AI can be integrated into your existing control architecture, enhancing, not replacing, your current automation systems. Once you've identified a potential AI project, the next step is a structured approach to ensure successful implementation. Step 1. Data collection and preparation. AI relies on data, lots of it. The first thing you need to do is gather historical and real-time data from your machines, sensors, and control systems. Step 2. Model selection and training. After you have the data, the next step is to choose the right AI model and train it using that data. Whether it's a machine learning model for predictive maintenance or a deep learning model for visual inspection, the key is ensuring it can learn effectively from the data. Step 3. System integration. Once the model is trained, it needs to be integrated into your existing automation systems like PLCs, SCADA, or MES. This is where AI makes its impact by enhancing real-time decision-making. Step 4. Testing and validation. With the model integrated, rigorous testing is needed to ensure it works as expected in the real-world environment. Validation is critical to ensure that AI predictions are accurate and reliable. Step 5. Deployment and scaling. Once the AI model is validated, it can be deployed at scale, and the insights it provides can be used to optimize operations across the plant. By following these steps, you set up a clear, methodical approach to implementing AI in your automation projects and ensure a high chance of success. Data is the foundation of every AI system. Without good data, even the most advanced algorithm will produce poor results. In industrial environments, AI typically relies on data from sensors, PLCs, SCADA systems, MES platforms, and ERP databases. But it's not just about volume, it's about quality. The data must be time-synchronized, labeled if possible, and free of noise, gaps, or inconsistencies. For example, if you're building a model for predictive maintenance, you'll need high-resolution time series data from vibration sensors, temperature probes, or current monitors along with historical records of failures. For visual inspection, you'll need thousands of annotated images showing examples of both good and defective products. You also need to consider data flow. Is the data coming in real time? Is it stored securely? Can it be accessed by your AI platform? Finally, data pre-processing is key. Cleaning, filtering, normalizing, and aligning the data are all essential steps before it's fed into a model. In short, the better your data, the better your AI. Investing in data readiness upfront pays off in model accuracy and system reliability. Integrating AI into industrial environments doesn't mean replacing your existing control systems, it means enhancing them. At the core of most factories are PLCs handling fast, deterministic control tasks and SCADA systems providing supervisory control and monitoring. AI sits on top of these layers, offering insights that were previously invisible. For example, an AI model running on an edge device or in the cloud can analyze sensor data, detect anomalies, and send alerts or suggested actions to your SCADA dashboard. In more advanced setups, AI can even send recommended setpoint adjustments to the PLC via OPC UA or MQTT, allowing your system to adapt in real time based on predictive insights. Importantly, this AI doesn't override the control logic, it works alongside it. PLCs still ensure safety and precision, while AI adds foresight and flexibility. And because AI output can be visualized within your existing HMI or SCADA interface, operators don't need to learn new tools, they just see smarter insights. Successful integration means your automation infrastructure becomes more intelligent without disrupting what already works. When deploying AI in an industrial environment, one of the key architectural decisions you'll make is where the AI will run at the edge or in the cloud. Let's start with Edge AI. This means running AI models directly on devices close to the machines like embedded controllers, industrial PCs, or gateways. The advantage? Low latency, real-time decision-making, and no dependency on internet connectivity. Edge AI is ideal for tasks like anomaly detection, quality inspection, or equipment monitoring where immediate responses are critical. On the other hand, cloud AI offers virtually unlimited computing power and storage. It's perfect for model training, large-scale data analytics, and applications that require integration across multiple sites. In the cloud, you can train your models using massive datasets, run simulations, and manage global optimization strategies. Many industrial AI deployments use a hybrid approach, edge for real-time inference, and cloud for long-term training and data aggregation. Choosing the right architecture depends on your application speed requirements, connectivity, and data governance needs. As we bring AI into industrial automation, we also introduce new cybersecurity challenges that can't be ignored. AI systems rely heavily on data, and if that data is compromised, the model's output becomes unreliable. That's why securing your data pipeline is just as important as securing your control network. For example, if sensor data is manipulated or corrupted, an AI model may make the wrong prediction, potentially causing production disruptions or even safety risks. Another concern is model theft or tampering. Just like software, AI models can be targeted, especially if deployed on edge devices or accessed through open APIs. To address these risks, it's critical to implement encrypted data transmission, secure access control, and model verification mechanisms. Monitoring AI decisions in real time for unusual behavior, what we call model explainability and auditability, is also key to catching anomalies early. In short, AI integration must go hand in hand with a strong cybersecurity framework that protects your models, your data, and ultimately, your operations. While the potential of AI in industrial automation is enormous, there are still key challenges to consider before scaling adoption. First and foremost is data quality. AI models are only as good as the data they're trained on. Noisy, incomplete, or poorly labeled data can lead to inaccurate predictions and loss of trust in the system. Second, there's the issue of AI transparency. Many advanced models, especially deep learning, can be seen as black boxes, making it difficult for engineers and operators to understand how decisions are made. Without transparency, teams may hesitate to rely on AI insights, especially in safety-critical or regulated environments. Third is integration complexity. Fitting AI into existing control architectures, aligning with OT systems, and training staff to interpret and act on AI recommendations all require careful planning and collaboration. And lastly, there's often organizational resistance. Change management, training, and trust building are as important as the technology itself. Addressing these challenges early will significantly increase the chances of successful, scalable AI deployment in your operations. As AI systems make more decisions on the factory floor, it becomes essential to understand how and why those decisions are made. That's where explainable AI, or XAI, comes in. Unlike traditional black box models, explainable AI provides insights into the logic behind predictions, classifications, or alerts. This is especially important in industrial environments where engineers and operators need to validate outcomes and take action confidently. For example, if an AI system flags a motor as likely to fail, explainable AI can show which inputs like temperature spikes or vibration anomalies led to that prediction. In regulated industries like pharmaceuticals or aerospace, explainability also supports compliance. You can show auditors exactly how decisions were made, which data was used, and what logic was applied. XAI also builds trust. When operators understand the reasoning behind a recommendation, they are far more likely to act on it and even help refine it. Whether through visual heat maps, decision trees, or statistical models, explainable AI makes AI not just powerful but practical and transparent. As AI becomes an integral part of industrial automation, one of the biggest challenges companies face is bridging the skill gap among their workforce. Traditionally, automation engineers have focused on PLCs, SCADA systems, and other control technologies. But with the rise of AI, there's a growing need for expertise in data science, machine learning, and AI systems. The transition requires upskilling existing staff, ensuring they are comfortable with AI tools, and fostering a culture of continuous learning. This doesn't mean that traditional skills are irrelevant. In fact, the best results come from blending OT expertise with IT and AI knowledge. The key is to build cross-functional teams that combine the domain knowledge of engineers with the technical skills of data scientists and IT specialists. By creating training programs, encouraging certifications, and offering mentorship, you can develop a workforce that's ready for the next wave of AI-powered industrial transformation. In the next section, we'll discuss how companies can manage this transition and prepare their teams for AI's growing role in manufacturing. Implementing AI isn't just a technical shift, it's a cultural one. And that's why change management is critical. Even the most accurate AI model won't deliver value if people don't understand it, trust it, or use it. Start by engaging stakeholders early. Involve operators, engineers, and managers in the design and testing process. Show them how AI helps, not replaces, their expertise. Clear communication is essential. Explain what AI is doing, how it's making decisions, and how it will impact daily workflows. Offer training tailored to each role. An operator needs to know how to interpret AI alerts. An engineer might want to understand how the model was trained. It's also important to define success metrics up front. When people see the tangible benefits like fewer breakdowns, less scrap, or faster inspections, they are more likely to support adoption. Remember, AI adoption is a team sport. Technical excellence matters, but human alignment is what turns a pilot into a lasting success. As we look ahead, one of the most exciting developments in industrial technology is the convergence of AI and the Internet of Things known as AIoT. IoT connects your machines, sensors, and systems, generating massive amounts of real-time data. AI turns that data into actionable insights. Together, they form intelligent, self-aware systems capable of making decentralized decisions and adapting in real time. In an AIoT-enabled factory, machines can not only sense their environment, but also learn from it. For example, a vibration sensor connected to an AI model can predict motor failure before it happens, triggering an automatic order for a replacement part. AIoT also powers autonomous control loops, allowing processes to optimize themselves without manual intervention. And with cloud and edge computing, these systems can scale across entire production networks, creating a fully connected, fully intelligent industrial ecosystem. AIoT is the foundation of the smart factory, where every device is not just connected, but learning, adapting, and evolving. Imagine a machine that not only detects when something is wrong but takes corrective action without any human involvement. That's the vision behind self-healing systems. AI is making this a reality in industrial automation. By combining predictive analytics, fault diagnostics, and automated control, machines can now monitor their own health and trigger preventive actions before failure occurs. For example, if a conveyor motor shows signs of imbalance, the system might automatically reduce speed, reroute production, or recalibrate itself while alerting maintenance teams. In more advanced setups, autonomous systems make broader decisions like rerouting material flow across different machines to avoid bottlenecks or failures. These systems adapt to changing conditions in real time, improving resilience and uptime across the entire operation. This is where industrial AI moves beyond decision support and into autonomous control. It's a major step toward factories that can optimize and repair themselves with minimal human intervention. While we're still early in this journey, the foundation is already here, and it's changing the way we think about maintenance, control, and system design. Generative AI isn't just for text and images, it's rapidly becoming a powerful tool in industrial design and simulation. In manufacturing, Generative AI can create thousands of design variations based on specific constraints such as material use, strength, weight, or cost. For example, if you need a lighter bracket that can still handle a specific load, AI can instantly generate options that a human designer might never consider. These designs can then be tested virtually using physics-based simulation tools, significantly speeding up the prototyping process and reducing physical waste. In automation, generative AI also helps design optimized control strategies, floor layouts, and even robotic motion paths. AI-powered simulation environments allow engineers to train and test AI models and digital twins before deploying anything to the shop floor. This not only reduces risk, but also shortens the time between concept and implementation, bringing agile development into industrial design. Generative AI is helping engineers move from design and test to generate and validate, transforming both how we innovate and how fast we get there. One of the most forward-looking applications of AI in manufacturing is the rise of autonomous production cells. These are compact, self-contained workstations equipped with robotics, sensors, vision systems, and AI that can perform entire sequences of tasks independently. Unlike traditional production lines, which require coordination across many machines and human operators, autonomous cells handle everything locally, detecting materials, assembling parts, inspecting quality, and even adjusting their own processes. For example, an AI-powered cell might assemble electronic components, detect a faulty part, and autonomously rework the process or switch to another task all without operator input. Because they are modular and reconfigurable, these cells are ideal for high-mix, low-volume production, rapid prototyping, and agile manufacturing environments. They can also be scaled horizontally, deployed across the factory floor, or distributed across locations, making them a key enabler of decentralized, resilient production. Autonomous production cells represent the convergence of robotics, AI, and edge computing, offering a glimpse into the factory of the future, where flexibility and autonomy go hand in hand. As we look to the future of industrial automation, several key trends are shaping the next generation of smart manufacturing. First, the convergence of AI and IoT. IoT is creating self-aware systems that adapt and respond in real time. Next, we're seeing the rise of self-healing machines and autonomous systems where downtime is minimized and decision-making happens without human input. Generative AI is accelerating design and development cycles, helping engineers create and test optimized components and processes in virtual environments. AI-powered autonomous production cells are making factories more modular, flexible, and decentralized. We're also seeing greater emphasis on explainable AI and trustworthy AI as transparency becomes critical in safety-critical and regulated industries. And all of this is driving a shift in workforce skills, organizational strategy, and digital infrastructure. The opportunities are vast, but they require readiness in data, in culture, and in vision. The good news? The technology is here. What's needed now is leadership and action to bring these trends to life. Let's wrap up with a few key takeaways from today's session. First, AI is not a replacement for automation, it's an evolution. It builds on existing control systems and enhances them with prediction, adaptation, and learning. Second, value starts with data. The more structured, clean, and accessible your data is, the faster your AI initiatives will succeed. Third, start small and scale fast. Pilot projects are your proving ground. Once value is demonstrated, expansion becomes easier. Fourth, human alignment is essential. Successful AI deployment depends as much on trust, training, and teamwork as it does on the model itself. And finally, AI is already delivering real ROI, from reduced downtime and better quality to faster processes and smarter decisions. Whether you're in maintenance, engineering, IT, or management, now is the time to explore how AI can enhance your operations and sharpen your competitive edge. So, how do you move from ideas to action when it comes to AI in your industrial environment? Here's a practical roadmap. Start by identifying a high-impact use case. Look for areas where downtime is costly, quality inspection is manual, or process optimization is challenging. These are great places to apply AI. Next, focus on a small, contained pilot. This could be a single machine, production line, or inspection station. Define clear success metrics like improved uptime, fewer defects, or reduced energy use. Then, gather your data and domain experts. Ensure you have clean, usable data and involve people who understand the process inside and out. Collaborate with internal teams or external partners who have experience in AI implementation. You don't need to build everything from scratch. Finally, treat your pilot like a learning exercise. Document results, gather feedback, and iterate. If the pilot works, scale it. Getting started with AI doesn't require a big budget or massive transformation. It starts with one use case, one model, and one win. To implement AI effectively in an industrial setting, you need the right tools and platforms, ones that are scalable, compatible, and tailored for your operations. On the development side, frameworks like TensorFlow and PyTorch are widely used for building machine learning and deep learning models. If you're looking for more engineering-focused platforms, MATLAB is a strong choice, especially for signal processing, simulations, and control integration. For cloud-based solutions, Azure Machine Learning, AWS IoT, and Google Cloud AI offer powerful infrastructure for data processing, model deployment, and real-time analytics. On the industrial side, platforms like Siemens MindSphere, Rockwell's FactoryTalk, and GE's Predictive provide AI integration directly into industrial ecosystems. You'll also need tools that bridge the gap between AI and control like OPC UA gateways, edge devices, and data historians. The key is choosing a stack that matches your data environment, system architecture, and long-term goals while keeping your team productive and aligned. Remember, the best tools aren't the most complex, they're the ones your team can deploy, trust, and scale confidently. As AI becomes part of the industrial toolbox, engineers need to evolve their skill sets to stay competitive and relevant. Start with the fundamentals, understanding machine learning concepts, data pre-processing, and the basics of Python programming, which is the most widely used language in AI development. For control engineers, learning how AI interacts with PLCs, SCADA, and edge computing systems is critical for successful integration. You'll also benefit from hands-on experience with AI platforms and tools, whether it's building models in TensorFlow or deploying them via cloud services like Azure ML or AWS. But technical skills aren't the only requirement. Engineers in the AI age must also be comfortable with cross-disciplinary collaboration, working alongside data scientists, IT teams, and business leaders. Understanding how to frame industrial problems in a way that AI can solve and how to interpret AI-generated insights will be essential skills. AI is not replacing engineers, it's empowering them. The more fluent you become in both automation and AI, the more valuable you'll be in the smart factories of the future. So now that you've seen what's possible with AI and industrial automation, what's next for you and your organization? Start by evaluating where you are on the AI maturity curve. Are you collecting data? Are your systems connected? Have you run any small pilots? Then, pick a use case that aligns with your business goals. Whether it's predictive maintenance, quality inspection, or energy optimization, choose something measurable, valuable, and feasible. Bring together the right stakeholders, OT, IT, data, and operations, and align them around a clear outcome. Most importantly, commit to continuous learning. AI is not a one-time project. It's a journey of testing, improving, and scaling. Every AI success story starts with one small step, a single use case, a focused team, and a willingness to learn. So take that step, because the future of industrial automation isn't just automated. It's intelligent. Thank you for joining today's session on AI in industrial automation. I hope it sparked new ideas, clarified key concepts, and gave you a clear path toward implementing AI in your operations. As we move forward into the era of intelligent manufacturing, the ability to combine automation with data-driven decision-making will become a key differentiator. Whether you're exploring your first AI pilot or scaling existing systems, remember, success comes from aligning technology, people, and purpose. If you have questions, now's the time to ask. I'm here to help you explore your next steps. You can also reach out after the session via LinkedIn or through InnerAutomation if you'd like to continue the conversation or collaborate on a project. Thanks again, and I wish you success on your AI journey.